Okay, so what we are looking at here in Photoshop is our L5 Triheximal Holonic compute stack. Try to get that down to a much easier phrase for people. But the basis of this idea, you can read the blog post for it. The basis of this idea is to create a graph or a structure in 2 dimensions that represents a 3-dimensional structure in which I can put computers or sensors or whatever, whatever it is that I wanted in each of these holons, so to speak. For those of you who don't know what a holon is simply it's almost like a fractal, but not. It's one something which is like the whole that it exists inside of, and inside of it exists smaller and smaller copies of itself. Um, and the fact that it's interconnected, right? It interacts with its environment, the environment being the black space in this equation, and it interacts with all of the other holons. And the result of that interaction that you're seeing are these colors. So I just wanted to note quickly in this video a couple of interesting things about. So basically, what this is it's 5 levels, right? 1, 2, 3, 4, 5, and or you can count it like this: 1, 2, 3, 4. Now, why does that count from 5 this way and 4 this way? Because this is actually negative space. This looks like a cube, but it's not a cube. It's just the place where the 3 red, green, and blue hexagons of each holon meet. And because of a hexagon, if you notice, like, this looks like a hexagon as well, if you don't look at it as 3-dimensional but 2-dimensional. So the idea behind this whole thing is that first off, I just to make this specific one, all I did was I created the 3 first big hexagons, right? Red, and I colored them pure red, pure green, and pure blue. And then I put them in Photoshop using a linear dodge filter, and I put them in front of black, and I made them 50% opaque. So that means that what you see here is 50% blue. And since these are stacked on top of each other, this is 50% blue, that's 75% blue, that's 88% blue, which is really 87.5. That is 12.5 divided by 2, 6.25 extra. So instead of 88, it's 94 or something like this, around 94. Now, basically, what you're seeing here, I flipped this around. What I had before was the opposite, right? And you get the same effect, but the cube is upside down, so I moved it this way. Or rather, it looks like it's the inside of the cube rather than the outside of the cube. So this way, it just looks like they look like full cubes, because even though it's negative space, the interesting part about it is that if you were to put an actual, let's say that this was a multi-leveled computer, and on each level was a processor that all it did was add a color, or be a color filter. One color filter is blue, one color filter is green, and one color filter is red, right? So this would be roughly the result of the data that it would see if you were looking at black. And so one thing that you'll obviously notice right off the bat is that there is there's that weird triangle looking, what they call a fractal, which is really just a holon. A fractal is just an image of a holon that's flattened by some dimension, right? It leaves a dimension out when you're rendering it into an image. So the thing is that this is a representation of the data itself, right? But it's also an image because I like art. So as you can see, if you were looking at the negative space, this negative space actually has data in it. These cubes that you're seeing are the 3 addition results of each of the holons on each level. So if these 3 big holons are level 1, we are on level 0 perceiving it, right? Like imagine that this is actually inside of another big level, right? And that can just keep going forever in one direction and smaller in the other direction as well. This is 2-dimensional map, so it's limited, which also causes an effect. And so your green is going to be, so okay, for those of you who don't know a little bit about color theory, we'll just look at it this way. You can look at it in a couple of different ways, right? There is HSB, RGB, Cmyk. All of these are just different processes, different equations in order to compute the same color, right? But these are, Photoshop shows how it's expressed. Okay, so if you start out in the center, so this is pretty much, this represents the exact offset, the color offset of each of the levels, right? So this is like a piece of data that can be used by which to calculate the rest of the data if you know it. So for instance, this hexagon in the middle represents the data coming in to level 0 from level 1, right? And this one represents the data that's coming in from level 2 to level this one represents the data that's coming in from level 2 to level 1, and this is level 3 to level 2. Okay, so also if you notice, like this is, so I'm just going to show you a couple of different examples of how this interesting little thing works if you hop around on the negative space looking at the data that each level represents. Now this is a negative space, right? What this, in the positive space, it's actually, it has data too. All of these colors that are in the positive space are the output of the colors that exist on this level. So every color that is above red, 50% red, right? So I'll just click on this. Red 128. RGB is a scale from 0 to 255. So 128 is in the center, right? That's 50%. Or you can see 50% brightness, right? HSB takes the same idea and makes it hue, saturation, and brightness. So like you're looking at what color it is first, and then you're looking at how gray it is, and then you're looking at how black it is. This one, Cmyk, is a one that's based off of a color theory by a dude who spent like 40 years studying color and writing a book about it. And the idea is that there's cyan, magenta, and yellow. And his idea is that every color, oh, and then K is black in Cmyk color standard. So his idea is that there's really only 2 colors. There's light and there's dark, right? But our eye splits the colors into what we perceive as red and blue. Now, this is obviously red and blue that's very close to black. So it's much darker than like 50% red or blue. But the thing is that the way that this color scale works on Cmyk is that cyan is 100% blue and yellow is 100% red. Magenta is just like a mix of blue and red. Or something along these lines. Like there's also different color schemes that people have created since this guy made his thing. So there's like, some people say that there's cyan and magenta, and yellow, and everything's just a mix of that. But some people say that there's just 2 colors, and green is an effect that our eye perceives. So, and then there's like more brightness or less brightness. So yeah, it could be CMG, K. You could even look it up in Wikipedia and find a whole bunch of crap about it. Anyway, so the idea here is that we're going to go in and we're going to do some, let's just say, interdimensional computing. Right? We're going to take the whole idea that if you draw a line or you hop from one point to another using the data streams, right, using this negative space that we call it, or what looks like a cube, you'll see some interesting information along these lines, right? So first off, let's take a look at what if you just go in a straight line in any of the directions, right? There's three directions: green, red, and blue. So let's go blue, right? So that's 128 blue at 50% brightness, 240 saturation, and the cyan we've got 100%. Let's put this over here so we can see where we're going in blue. By the way, I also love this like little mountain effect. If you were to travel along these lines or in a spiral, you can really travel through this information in any way that you want and get data out of it, get a color out of it, basically. So, and you can get a sequence of colors that is sequenced based off of the way that you travel through it. So, for instance, you've got blue here, 128 blue, right? So that's medium blue. Then you've got, so if I hop from this cube's blue to that cube's blue, because this dimension is just all blue, right? So I'm hopping from this blue's cube to one dimension, one level down of blue, which means instead of 50% brightness, since I'm adding half blue to blue, it's actually 75%. So I'm getting half of what I had before, closer to white, or basically closer to 100% blue. Sorry, closer to the brightest blue that you could possibly imagine, right? Which is an infinity. And the rest of this white is actually an illusion caused by the infinity of ultimate brightness. So each of these ones goes off into infinity in this direction, towards 100% that color, but going in smaller and smaller steps, going in half of its distance the entire time. So we've got blue over here, bam, bam, 75. Next one is 88. Same sort of idea, where we're doing half and half again. So this is 88. This one is going to be 94. So my math was right. And then this one is going to be 97%. And this one actually doesn't exist because we don't go that far down in the compute stack, right? So we've got 1, 2, 3, 4, 5. Okay. Now, let's imagine that we wanted to go in a different direction. Let's say that we want to start off at level 2. So we're starting. So okay. So one thing you should also have noticed is that in the blue here it went 128, 192, 224, 240, 248, 252. Yeah, 99% bright. So that's almost there. But any higher than that, you're not getting any resolution. So we can't even really see the difference on a computer monitor, and probably not even with our eyes between those two different shades of brightness of blue. Since we're starting at 50% here, it's much closer approaching. It's much more quickly approaching blue. But we could start at 25% opacity of everything, and or of all the holons, right? And they would add 25% of the color to each color that's in its context, which is the color that's surrounding it. So the color that's surrounding all of these holons, these three paired holons, is on this level 1 is black again, and the color that's, you see these right here, the red, the blue, and the green, the color that's surrounding them is 50% blue. So basically, now that I'm inside of 50% blue, I'm never going to go below 50% blue, right? And if I were to go on this one, I would never go below 75% blue. So 50% blue, 75% blue, and so on. Right, okay, that's pretty interesting. But what if we wanted to calculate something more interesting, something that gives us a less linear or quadratic equation, right? Let's say we want something that's going to get us some thing which seems random, okay? So if you notice on level 5, all these are like what? Super small super small hexagons, okay? So if you take this hexagon and you see here, there's a line that goes down, bam, 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 exactly like this, okay? Now, this line, it goes from green all the way, so it goes from the closest that this graph can approximate to green to the closest that this graph can approximate to blue. But it doesn't go through any orthodox means if you try and follow just a line directly through it, right? You go, this cell holds 252, so in 99% brightness, right? So that's, since we're pure blue, 99% brightness is like 99% blue. But there's actually 97% brightness here, and as you can see, since we've gone one green up, we have now gone 50% from 0 in green, which is why you see this weird jump from blue to that. Now, if I click here, it's the same color. It's the same color because this is blue of green and this is green of blue. So blue of green and green of blue is the same color. But in negative space, the stepping is different. But in positive space, green and blue are green of blue and blue and green. So the order of the components does not affect the product. In single level linear space along the edges. Okay, and going through barriers. So from one side of the barrier we've got one color, and the other side of the barrier we've got the same color. Then here we've got, what do we have? So this is 192 240. This is 128 248. So it is a slightly different color, slightly more green. If we look at the hue, 240 is blue, right? Or it's rough, it's close enough to blue. But 209, 209, 192, 209, 192, 192, 180, 209, 192, 192, 180, 192, 180, 180, 168. Wow. So following the output of the hue filtering on this, or following the hue outputs this sequence, which is almost like binary. Like if you were to look across one binary dimension, so to speak, but this is trinary. So let's just say that this is 240 is A. So we've got A, B, B, C. B. A, B, B, C, B. C. C. D. So the smaller and smaller we get along, if we were to make if you were to take this whole image, do the math again, and put this inside of one of these level 4 layers, we would see the actual something way more approximating to what this actually would look like if calculated. So you might notice that so it's what, A, B, B, C, B, C, C, D, B. It's just that this looks almost like a different color because of its context, and so our eyes, the way that it processes it, makes it look different. Anyway, so so A, B, C, 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 180, 209, what, 168, 180, 180. Huh. I'm gonna have to write this down and put down the pattern. And this is probably going to be the same going this way, but in a different direction, right? We've got 240, 240, 271, 271, 288, 271, 288, 288, 300, 271, 288, 288, 300. And if you count to the RG and B, B252, R128, B248, R128, B248, R192, B240, yeah, it makes a little bit more of a pattern inside of HS and B than it does inside of the RGB space once you're de-dimensionalizing the output data by selecting a point and grabbing the color from it. So what I'm doing basically is just, instead of just looking at the color itself and going, hey, what a nice color, I'm putting it through these filters so that, well, these are just basically conversion algorithms, so that the space can be mutated or the space can be transformed into a different space, which makes a little bit more sense to me on a linear basis, because lines are easy. All right, so we've done this hop from here to here. We've done the lines across. Now what if we were to do a spiral? Let's look at a spiral and how things change. So I'm starting with blue. This is obviously going to be the same in any direction as long as you go in the same relative direction. So I'm going to start with green, right? But instead of going in the green area, I'm going to go green. I'm going to go down blue into green. Or on green, right? So this is cyan. Then, if I were to go up, that would be more green again. And one thing to notice about this is, if I was going to draw a line between here and there, look at this weird color palette that it brings up if you go down the levels. So we've got level 2 here, this nice magenta, pure 50% magenta. Then we've got gray, which is actually, if you look in the center here, shows up there as the analogous. So we've got gray. But then you've got this greenish gray. So it pulls it into green. So it pulls magenta into green through gray, going down the scales. So if you're imagining that instead of me using Photoshop, whatever, I'm actually another one of these things, but I'm the one that sees this big, nice, beautiful RGB hexagon as data, and I'm 1 compared to the 3, compared to the 9, compared to the so on and so forth, the 27. Anyway, So there's a lot of interesting stuff that's inside of here, and you can look at the context of the background color, and how this changes everything, if you were to change the background color. But that'll be another video because this one is already way too long. Until next time.